Hello, so today I'm going to be talking about hfoGUI. HFO stands for High Frequency Oscillation, so it's a graphical user interface that was designed to visualize high frequency oscillations within our in vivo electrophysiology data, recorded specifically using Axona's dacqUSB, so it has to be in the Tint format. So if your data is not in the Tint format, this GUI might not be useful for you, just a warning. This is a Python package, so you have to have Python installed. I have this Python virtual environment running with Python 3.7. I tested in 3.7. That's what I work with, so it should work with many of the other Python versions. However, if you find some issues, likely because I haven't tested on that Python version, feel free to email me. Let's start by downloading it. So we can download it using pip install. So we'll do python -m pip install hfoGUI. Make sure the GUI is capitalized. That's very important. Press enter, and we'll see it begin to grab all its dependencies. It uses PyQt5 as the graphical user interface framework. PyQt5 is cross-platform and works with, or it's compatible with many of the Python versions. So it should be fine for you to use other versions of Python as well as Linux and Mac. I just haven't tested them. So the packages should finalize installing soon. It does use PyQtGraph as a way to enhance the visualization, make it faster. All the packages have been installed now, so we can just run it using python -m hfoGUI. This is what it looks like when the hfoGUI has been opened. You should just see a single main window, and that's it, at least for now. Now to begin to visualize our data, we must first determine which session we want to visualize. So we'll import set, choose a set file. I have a set file on our desktop, so I'll navigate to wherever wherever your session is. Choose the session you want to analyze, then press apply. Once you press apply, this set file name text box should now be populated with your current session file name. Doesn't really look like much else has changed, but behind the scenes, it has populated some of these graph settings parameters. So we first have to manually add our sources that we want to visualize within this main menu. So we open up this graph settings to do that. Now I provided a multitude of parameters that you can play around with. It's grabbed all the sources. So looked through your session and found all your EEG and EGF signals. That's mainly what you're going to be looking at. When choosing a source, I generally choose the EGFs as it has a higher sampling frequency. So I'm just going to choose that one, especially since it was traditionally designed to look for high frequency oscillations. So you're going to need the higher sampling rate to visualize those. Now you have a few filtering options. I generally stick with Butterworth. Filtering types, if you want to low pass, high pass, or band pass it, feel free to not filter it at all. There's a 60 Hz filter. This is the filter order. I usually stick with a third order filter. That's the default. Mark peaks. So mark peaks will stick an indicator at every time point where there's a peak in your signal that you decide to mark the peaks for. So this can be pretty stressful for your computer to visualize if you have if you filter out all the low frequencies and there's just a bunch of high frequency activity, then you're gonna have a lot of peaks to visualize, and it's gonna slow down. So I tend not to do this, but I mainly put it in if you're gonna look for phase locking or something. It's a good visual indication of phase locking. Maybe you're trying to determine if the peaks of this theta signal phase locks with the peaks of the high gamma signal. And you might put the mark peaks on the theta signal just to visualize it. Gain, that's pretty standard. If you want to multiply the signal by 2, the amplitude of the signal by 2, you put a 2 here. If you want to, if one of your signals is taking up too much of the screen and you want to decrease it, feel free to set this gain to 1/2 or whatever. This Hilbert option will just plot the Hilbert transform on whatever signal that you want to apply it to. I generally use it for visualizing high frequency oscillations. So if you're not doing that, then there's really no reason to have this checked. I can show you what it looks like right now, actually. So let's add a bandpass signal from 80 to 250 or so, and let's apply a Hilbert transform for this just to show you. We'll add this source, and it's gonna calculate the signal and then plot it here in this main menu. So we see that this red signal is the Hilbert transformation. This blue signal is our filtered signal. Now, let's add another signal. We'll do EGF again, Butterworth, that's fine. Bandpass again, this time from 250 to 500 Hertz. We won't Hilbert that. Add graph, and now it's gonna replot on the main menu, on the main window. It's gonna show two plots this time. This one is our original one, and then the second one we just added from 250 to 500 Hertz is the top one. Let's just add a final signal. For now, it will just be a raw signal just to show us what the raw signal looks like. Add source, and now we're gonna add 3 plots on the main window. Okay, now this could be a case where you might want to change the gain. So, say theoretically this third signal is taking up too much of the screen. You have the option of updating any of these signals that are on this list, as well as removing them and adding a different one. If you feel like you may not need a signal anymore, you can remove the signal. But right now we're just going to update the signal. So if when we selected this, it populated all the options with what we chose here. So there should be no filter, there's no cutoff options, it's not marking the peak, etc. And we're going to just update this gain to have a value of 0.5, and then we're going to update the selected graph. It's going to replot everything as you've been seeing. And now the overall amplitude of the raw signal has been decreased by half. So that is all the graph settings options. Feel free also, if you tend to use however many signals, if you have a standard method that you just tend to use, feel free to save the profile. So if we like this 3 source and these options that we chose earlier, we can just save it as test profile or whatever profile name you want to choose. Press OK, and then whenever you load the next session, you can just simply choose test profile and load this profile, and it'll populate the main window based off of these exact settings that you saved. Okay, now that is the end of the graph settings window. At the bottom, I provide the scroll bar, so if you were in the mood to visually and manually look through all your data, then you can feel free to just scroll through the data. And however, if you know that there's a certain time point that a specific signal is that you want to look at, feel free to put in that time point, and it will bring you right to there. The window size can also be changed, so I have a default to half a second, but maybe you like to view 1 second of the data. Feel free to change that to 1 second. Now, let's see if we can scroll down and find anything interesting. Okay, so maybe this signal is interesting. It looks like a high frequency oscillation. Let's see. So since this tool was initially developed to visualize high frequency oscillations, you have to be able to visualize the time frequency representation of these signals. So I have TF plots, meaning time frequency. So I've made it so you can select this signal by pressing on the left button on your mouse. And if you open up the time frequency plots, you will see this time frequency representation of the signal here as a Stockwell transform. So we have the raw graph, we have a filtered graph here from 80 to 500 Hertz, and we have the time frequency representation. So the red colors, or the warmer colors, represent frequencies that dominate the signal. Essentially, they have the most power in the signal, and the blues and the colder colors represent frequencies at the specific time points that don't really contribute to the signal. So here we have what looks like at about 500 or 450 Hertz. There's another tab, this power spectral density tab, which will take just the slice where the cursor is at and look at the frequencies, the powers of the frequencies across that one time point. So here we see that around 475 or something is the peak frequency of this signal. So this is what I use to calculate the peak frequency of an event. So here is about 475 Hertz signal, which is a fast ripple, or that's how I identify a fast ripple. Everyone has varying opinions as to what a fast ripple and a ripple is. This is ours. Now theoretically we can save this for later by adding, by scoring the session. So if we open up the score window, we're able to add events of interest that we find along the way. So if we say that this whole window here is our interesting event, and it requires a score name, just so people later who come across this signal know who scored it what. And it requires a score, so let's just give it a fast ripple score. And we can add this score here. It saves as an ID of man1, meaning manual 1, and it saves the start and the stop time of this event. So you can imagine you can go and find many events. Say you're not looking for high frequency oscillations, but instead you have the sources for theta signal, and then you have the high gamma band filtered and a raw band. So you're looking at maybe phase locking of theta and gamma. You could, if you find an example where the phase locking looks really good and you might want to include that in a manuscript, then feel free to, I mean, this isn't a good signal, but feel free to just select that signal by dragging the cursor, going into your score tab, and then just saving it as whatever you want to save, theta or whatever. We just add the score, and now we have our events piling up that we can go back and visualize later. So a majority of what I discussed has required some manual input. There is some automatic detection, as you can see from this tab, and it is mainly for high frequency oscillations. Feel free to fork the hfoGUI on GitHub and add your own automatic detection. If you have automatic detection for whatever events you're trying to visualize within this GUI, feel free to add it there, and you can use that here. What we do here is we find EOIs. EOIs means events of interest, and these are just parameters specifically for finding high frequency oscillations. I can provide references as to what this is, but if you're familiar with Ripple Lab, they pretty much use this same thing. We just press analyze here. Now I don't have a dialog that pops up. Theoretically, I should provide a dialog that shows you the progress of the signal, but it does print outputs into the console. So for now, if you are using this tool and this functionality of this tool, feel free to just look in the console and it'll tell you how much of the data has been completed. So now you see that once the analysis has been completed, this list has been populated with all the automatic events. Hill is for Hilbert. It uses this Hilbert method of detecting the signals, and it's the same as essentially the same format as the score tab, but these are just automatically populated. So we can go and say one of these signals. Let's look at this one. If we look at the time frequency representation, and we find that, okay, this is around 200 hertz. Yep, maybe like 190 or something like that. That is theoretically, with the literature that I agree with, this is theoretically a ripple. So maybe we want to include this as a ripple. We can select this option as ripple, make sure we're on the correct event, and then we can add the selected EOI to score. So this will move Hill 3, which is what I was identified as, from this list over to our score list. So in short, the scores are the score tab contains all the confirmed scores, and these are all hypothetical ones that you may or may not want to save. You can save them if you haven't finished scoring the session and you want to look through the rest of these signals. You can save them, and in turn you can load them the next time you load the session. And same with these scores, we can go and save these here. Let's save them as HFO scores. Okay, and then if we deleted them all here, we can test that our save has been completed by loading this HFO scores file, and we get the same IDs that we just deleted. Okay, so that pretty much wraps it up for this HFO tutorial. I will have a written version of all of this on my website, so feel free to check that out in the description. and you should if there's it will go more in depth as to each of the topics. So if there's something that I glossed over, you might be able to find it on the website. Also, feel free to contact me if you want to learn more, if you have a question. Thanks for watching.